Hello everyone, my name is Kishan Agarwal from CSC B section. Today I am going to present my Tech Talk video of physics. The topic is machine learning aided optical fiber communication system. So let's begin with the topic. So first of all, we see what is fiber optic and why it is used. The fiber optical network offers high speed, large bandwidth and a high degree of reliability. However, the development of optical communication technology has hit a bottleneck due to the several challenges such as energy loss, cost and system capacity approaching the Shannon limit. As a powerful tool, machine learning technology provides a strong driving force the development of various industries and greatly promotes the development of society. Machine learning also provides a new possible solution to achieve greater transmission capacities and longer transmission distance in optical communication. In this video, I am going to introduce the applications of machine learning in optical communication network system. So just introduction about the optical system. Recently, we have witnessed rapid development of the network technology like software defining networking, 5G, and the emergence of new applications like high definition video, Internet of Things, IoT. As the network application increases, so due to the demand for the network bandwidth also increases. For example, the optical bandwidth for a high quality 4K is higher than 20 MB per second. The current compound annual growth rate of global data traffic is close to 30% per year. The continuous development of massive data services has created higher demands and challenges for the transmission capacity, access bandwidth, and system power consumption of optical fiber communication systems. Traditional algorithms are relatively inefficient and cannot solve the challenges of energy loss, cost, and system capacity approaching the Shannon limit, due to which the development of optical communication technology is being delayed. To mitigate some of these challenges, it is essential to introduce new technologies to optimize the optical communication transmission performance, improve the efficiency of energy distribution, and reduce the system complexity. With the great success of machine learning, applying it in new networking has drawn considerable attention. Machine learning can learn potential patterns and relationships from experience without being explicitly programmed. Through repeated trial and optimization, the learned strategy can gradually converge to the optimal solution. Compared to traditional heuristic methods, machine learning methods are more efficient and accurate. Therefore, a machine learning algorithm is potential key in the high-speed optical communication environment. Though the establishment of a model for dynamic prediction of the entire environment, machine learning algorithms can bring a huge computing power advantage by greatly improving the efficiency of signal transmission and processing. In the entire transmission process, many steps can be optimized by machine learning methods. For instance, the characterization of operations of the transmitters, optical amplification control, modulation, format recognition, linear impairment identification, and monitoring, mitigating of non-linearities, and estimation of the transmission qualities are suitable options. However, many kinds of existing machine learning technologies are effective for these steps. So this is an image showing how machine learning takes raw images and how it is transmitted from using optical communication. Raw image, then deep convolutional network, neural network, and reconstruction of the image takes place. Input image is this one. So next, logical architecture of the 5G network layer includes the three functional planes: forwarding, control, and access. These planes are responsible for the connection, establishment, operation of intra-data center optical network failure or fault detection, and proactive restoration and other functions. Together they support the operation of the entire communication network. While the implementation of machine learning technology can address linear and nonlinear damage well, most current machine learning algorithms are still only suitable for standard quadrant constellation diagrams. Recently, probability shaping (PS) technology has greatly developed the transmission capacity of optical communications, enabling it to be closer to the Shannon limit. But these algorithms cannot adapt to the signal model after probabilistic shaping. In terms of optical network construction, the solution to the lack of channel resources is the use of hybrid wavelength division multiplexing and time division multiplexing. Passive optical network structure. This structure can allocate redundant resources, deploy multiple backup switches and backup optical fibers, and switch to backup system when channel capacity is inefficient or affected by a failure to ensure normal use. However, due to the deployment of ultra-dense millimeter wave remote radio head RRH in 5G, the use of an HPON architecture to support millimeter wave RRH, that is remote radio heads, will be expensive. Furthermore, traditional wireless routers do not have sufficient processing power to transmit millimeter wave signals, and the deployment of millimeter wave routers introduces huge additional costs. Therefore, the traditional solution is not compatible with the utilization in high speed and large capacity 5G centralized radio access networks with millimeter wave based remote radio head networks. Now, our discussion can be divided into three sections. In this following section, we introduce the k-means clustering algorithm to compensate for the nonlinear effects in the probabilistic systems. Then we also demonstrate the principal component-based phase estimation algorithm to correct the phase deviation problem in the PS system. Following that, channel resource allocation and the location selection of remote radio head in optical communication and wireless communication systems is discussed, and recurrent neutral network and genetic algorithms methods are employed to establish an optimization distribution plan. This is how the fiber optic cable or the light pipe works. It has a transmitter block and a receiver block. When the coder or converter waves are converted into digital pulses, and light source transmitter circuits, and these light turns or on off at a rapid speed, and these waves are carried by the fiber optic cable and transmitted to photocell or light detector, and then they are again converted into digital pulse, and decoder will decode it, and analog output will be given out. So let us begin with our discussion. K means nonlinear compensation algorithm in optical communication. To handle surge in network traffic, higher order modulation signals such as multiple phase shift keying and MRA quadrate amplitude modulation are widely employed to increase optical fiber transmission capabilities. These higher order modulation signals are easily impaired by various types of noise incoherent optical communication system. The existing digital signal processing technology can well compensate for linear damage such as chromatic dispersion and polarization mode dispersion. However, highly power signals will make the nonlinear phase noise caused by the Kerr effect evident because the NLPN nonlinear phase noise is difficult to eliminate. The nonlinear damage is a bottleneck for the development of high speed, long distance, large capacity coherent optical fiber communication system. At present, the research on channel modeling and nonlinear damage compensation in optical communications has a theoretical basis and experimental support. Recently, optical phase conjugation and the split step Fourier method (SSFM) and the Voltaire series nonlinear equalizer have attracted wide attention from the various scholars. The optical phase conjugation means that regardless of the symmetry of the power signal evolution, optical phase conjugation (OPC) combined with appropriate dispersion mapping can be used to effectively suppress the nonlinear effects in the fiber channel. It increases the upper limit of power, thereby raising the nonlinearity threshold in the long distance optical communication. The split step Fourier method uses the non-iterative asymmetric distributed Fourier equation to establish a mathematical model to solve the nonlinear Schrödinger equation, which can effectively improve the accuracy of the nonlinear compensation. The nonlinear equalizer is an algorithm based on the Voltaire series transfer function, which can improve the nonlinear capacity for a specific analysis link, but also this algorithm will greatly increase the computational complexity. The algorithms mentioned above can compensate for the signal distortion caused by the nonlinear effects to a certain extent, but their algorithm structures are relatively primitive and the complexity is relatively high. Optical signal will receive different kinds of noise effects in the fiber during the transmission process in the high-speed coherent optical communication system. Phase noise and nonlinear phase noise will have a major impact on the signal. These two types of noises are introduced below and solution using machine learning technology are provided. The NLPN caused by Kerr effect distorts the original square constellation so that the constellation points are not distributed in the original square constellation position. The k-means algorithm performs clustering processing on the received signal to find the position of each constellation point after the nonlinear effect. It then uses the found position as a new reference to make decisions based on the received signal. This greatly reduces the impact of nonlinear effects on the data transmission performance. However, the signal after PS cannot be simply applied to this method because the probability of each constellation point of the signal after the PS is different. When the optical signal to noise ratio is high, each constellation point is clearly separated, but meanwhile the nonlinear effect becomes more intense and the degree of distortion of the constellation diagram increases. At this time, the decision of k-means algorithm will ignore the low probability constellation points. This is because the number of inner circle constellation points is much greater than the number of outer circle constellation points, and the high probability constellation points are regarded as two clusters. This causes low probability constellation points to be ignored and high probability constellation points to be segmented. This cannot eliminate the effect of nonlinear phase noise, and it is also severely reduces the bit error ratio performance. To solve this problem, we optimize the k-means algorithm. The k-means algorithm weighs each constellation points according to the probability distribution of the constellation after the probability reshaping before deciding on the constellation diagram, and the weight of each constellation point in the inverse value of the occurrence probability. The weight value is substituted into the k-mean algorithm, which can eliminate the influence mentioned above in advance. The PS algorithm could be effectively reduce the BER of high order QAM signal overall and improve the transmission performance. In addition, when the input power was low, that is, input power is less than 2 dBm, the Kerr effect was not evident. After the k-means algorithm and the weighted k-means algorithm, the BER performance of the PS64 QAM signal were not significantly different. However, we can also see the performance of the weighted k-means algorithm was slightly superior to that of the k-mean algorithm. Whenever the launch power was high, that is input power was greater than 2 dBm, the BER curve shows that the input power increased, the BER of the k-means algorithm increased rapidly because the weighted k-mean algorithm could accurately locate the decision point. It could still stably determine the PS64 QAM signal. The number of iterations can represent the computational complexity of the algorithm. The complexity of the weighted k-means algorithm was lower than that of the original k-means algorithm, and when the input power was greater than 2 dBm, the complexity advantage of weighted k-mean algorithm was more significant. Although the steps of the weighting operations were added, the weighted algorithm had a faster search centroid speed and avoided false convergence. More importantly, when the traditional k-means process failed to converge correctly, multiple invalid iterations increased the computational complexity rapidly, and the weighted k-means algorithm could still correctly locate the cluster centroid in a reasonable number of iterations. Let us begin with the second one, TCPE phase recovery algorithm in coherent optical communication. Changing modulation and detection methods can improve the transmission rate. A traditional optical communication system can only transmit intensive modulated signals. When results in a relatively low transmission rate, the coherent optical communication system coherently couples the signal light with a beam of local oscillator light and then uses a balanced receiver for detection. The coherent optical system uses multiple dimensions such as amplitude, frequency, phase, and polarization to carry information. At the same time, it has a better communication performance than traditional systems, which can only detect the amplitude. In a coherent optical communication system, the optical signal emitted is loaded into an optical carrier and transmitted through the optical fiber to the receiving end. In a high-speed coherent optical communication system, the phase noise of the transmitter laser and the local oscillation laser is an important factor affecting the system performance. Because the phase noise will cause the constellation to rotate in the complex plane, the signal points cannot be distinguished. This will lead to incorrect judgment, thereby affecting the system performance. The feed-forward carrier recovery technology based on the classic Viterbi algorithm, that is VV algorithm, is widely used in the phase shift keying CSK modulation format, which removes the modulation phase of the data by calculating the mth power of the signal. Blind phase research uses multiple test phases to rotate in the constellation plan to find out the ideal constellation point with the shortest Euclidean distance from the input symbol to complete the phase recovery. The PCPE algorithm obtains a pattern with phase orientation by squaring the square constellation diagram. This is the main difference between the previous one and the PCPE algorithm. The principal component PC of these patterns is then founded through the principal component analysis PCA algorithm, since the direction of the PC has a linear relationship with the direction of the original constellation. The deflection phase can be found and the recovery can be completed. However, the algorithms described above have obvious limitations. Although the VV algorithm can better recover the phase of 4 QAM signals, the performance is relatively poor for higher order QAM modulated signals. The BPS algorithm can cope with the most modulation formats and has a better accuracy, but the DSP operation time increases too rapidly. The PCPE algorithm is only suitable for phase recovery of the traditional square constellation diagram and cannot be used for the constellation diagram after PS. This is the flow chart showing the PCPE algorithm. To complete the efficient solution to the phase recovery of PF signals, An optimized principal component-based phase estimation algorithm is proposed. This algorithm is applicable to recovering the phase of the high-order PS signal. The PCPA algorithm is an algorithm to realize data dimension reduction in the field of machine learning, which can extract important information from the complex data. In optical communication, phase information can also be extracted by using the algorithm. The main reason for the PCP algorithm not being applied to the system is that the occurrence probabilities of the constellation points with large amplitude are much smaller than those of the constellation points, and these constellation points are crucial for the PC algorithm to determine the phase deflection angle. In the OPCPE solution, the amplitude of the signal points that are closer to the center point of the constellation diagram in terms of Euclidean distance are scaled up and then superimposed with the algorithms or original low probability constellation points to obtain a set of modified constellation diagrams. In these constellation diagrams, the number of valid data that can be used for the PCA algorithm to determine the phase has been significantly increased. So this was about PCPE. Now let us see LSTM algorithm in traffic forecast and remoted radio heated location selection. Entering the 5G era, the traditional communication network architecture can no longer support the continuous growth of mobile broadband services. C-RAN is considered to be the most suitable architecture for the new generation of the internet due to the centralization, collaboration, cloud computing, and energy saving features. In this architecture, base stations are divided into two parts. The first part is the baseband unit pool and RHHS. The central computer room is merged into the BBU pool to complete most of the computing tasks. Thus, the centralized computing unit will greatly improve the resource utilization rate, thereby obtaining a significant performance gain and higher energy utilization. The RRHs are distributed around the antenna, which greatly reduces the attention in the connection between the antenna and the RRH due to the limited transmission distance of waves. How to choose the RRH location becomes a major issue. In order to meet user needed reduce resource base and increase anti-failure capabilities, it is necessary to propose a resource allocation model based on traffic prediction before RHS site selection. The traditional system rarely considers the RRS distribution method because the traditional scheme is to expand the capacity for each channel and design the resource allocation according to the maximum load. Although this solution can meet the needs of users under normal circumstances, it results in a considerable waste of resources and a poor anti-failure abilities. Machine learning algorithms are suitable for traffic prediction. Propose a deep neural network based prediction strategy to perform optical network traffic prediction. In a requirement network, neural network was used traffic prediction in the BBU pool. In addition, traffic forecasting in a virtual topology reconfiguration method was also found to be suitable method. The RRN is a deep learning algorithm that can be utilized to make predictions for time series data. Short-term memory as new type of RRN algorithm suitable for the building a real-time model. It stores information in a storage unit and sends it to the next step to complete the real-time data distribution plan. This is how LSTM network works, or it is a model of LSTM network. The LSTM algorithm was trained for traffic prediction. First, the long-term traffic data of each RRH was collected, and these data were used to train the LSTM network model in the cloud processor. The flows of the multiple consecutive time periods were input to the model to obtain the flow forecast for the next time period. Finally, according to the predicted time traffic model, channel resources were allocated on demand. The cloud processor calculated in the real-time traffic conditions for each RRH and ensured sufficient backhaul survivability and have high energy efficiency. To improve the energy efficiency, the RRH knew in advance how to use the minimum number of backhaul links to complete signal transmission in order to maintain sufficient backhaul survivability. Each RRH has a backup path. Once failure occurs, the backup path is employed to avoid the failure. An integer linear programming model can be used as an effective simulation tool to support the distribution of RRH in a small range. However, as the network scale increases, the computing time of the ILP model greatly increases. The GA can solve such problems quick and efficiently. So what are the advantages using machine learning in optical fiber communication, and what are the challenges using this? Machine learning algorithms are suitable for using optical communication system. The high computing power and the powerful modeling ability of machine learning algorithms can inject strong inputs into the further development of optical communication system. These are the advantages of machine learning. Yes. And stability of transmission. This is other advantage of machine learning. The main idea of machine learning algorithm is to learn through plenty of data so that the system can build a suitable model from it to solve related problems. This is indispensable in optical communication research. In the study of optical communication transmission layer, the most important step is to model the channel through the large amount of data collected in receiving end, so that the damaged data can be restored and reliable signal transmission can be completed. Machine learning is suitable for these steps as well compared to the traditional training sequences method or blind equalization algorithm. The machine learning algorithm can complete channel prediction more quickly and more accurately without increasing redundancy, and it can complete the real-time modification of the channel model through the newly received data. This significantly increases the stability of transmission. The other advantage is high computing power. The machine learning algorithm can provide high computing power, which is essential for the optical communicated systems. As the transmission capacity continues to increase, the amount of data to be processed also rapidly increases, which is a great test of computing power of the data processing center. The machine learning algorithm greatly improves the computational efficiency by establishing the most suitable model, frees up computing power and enables data centers to carry more businesses. This means that the stability of the optical communication network greatly increases, and it also lays a solid foundation for future network upgrade and expansion. However, the application of machine learning technology in optical communication system also faces some challenges. The main problem are the high complexity of machine learning algorithm and the lack of application research on the machine learning algorithm in the field of optical communication. First, the algorithm complexity of machine learning algorithm is relatively high, which is inconsistent with the development or direction of lightweight optical communication systems. When overall bloated system can only bring limited improvements in communication performances, this is no longer a suitable solution. When an overly bloated system can only bring limited improvements in communication performances, this is no longer a suitable solution. Several machine learning algorithms used in this article are relatively simple. How to apply complex machine learning algorithm to optical communication systems has become a new challenge. In addition, in the field of optical communication, the knowledge base of machine learning is incomplete. Building a high-performance machine learning model requires machine learning technology and feature engineering for specific fields and applications in the different fields. The knowledge bases are relatively independent. Although there are many machine learning algorithms for optical communications, large-scale research is still lacking in the entire field. Such considerable effort is needed to establish a mature professional machine learning knowledge base. In conclusion, machine learning technology plays important role in various fields because to its powerful performance, it also brings huge improvement to optical communication system. This article or this video briefly introduces applications of the K-mean clustering algorithm, PCPE algorithm and the genetic algorithm in the network system. we can see that these three algorithms optimizes the compensation of the nonlinear effects in the PS system, the correction of phase deviations, and optical allocation of resources in the optical communication network, respectively. The authors believe that machine learning technology will become an important means to break through the bottleneck of the optical communication and provide indispensable technical support for the further increase of communication capacity and improve communication stability in the future. Thank you.